Okay, so we're just going to do practice problems. Whatever you guys want to bring up is fine. I just want to start with this one as we're getting like, while you're working this, or if you don't want to work this and you want to look through your notes and see like what questions you have, either way. This one does end up being, you have to solve the quadratic formula. So like, I don't care if you just get it to the point of k equals whatever in terms of x. That's enough practice in my mind. We don't need to go through solving the quadratic since we're not going to do that on the exam. But this one is a challenge for other reasons, which is why I wanted to do it. So this is the only one I really want to do from 16. And then if no one else has any to volunteer, then I'll pull a bunch from 14 and we'll practice through those. Okay? So I'm going to put a hint up here. If you don't want to see it, don't look. But Okay, so the biggest thing here that you have to recognize is that you're going to use these equilibrium concentrations that they give you to start. Because they're equilibrium concentrations, you first use those to determine what K is. So I think this comes out to 20 if I remember correctly. Yeah. So the K value comes out to be equal to 20, and then you can use that for the rest of the problem. So in the rest of the problem, it says an additional pressure of Cl2 is added. So now we've kind of like knocked it out of equilibrium. So the Cl2 is 0.5 now in that case. And now technically we would have to solve for Q here and decide which direction the reaction goes. Now, I know intuitively if it was already at its balance point and we added stuff to the reactants, it's like a Le Chatelier's principle. Exactly. It has to go towards the products. So you can either predict it that way and say, I know it has to go towards the products, or you can go ahead and solve for what Q is. And if nothing else, this is a good practice for how to do that Q versus K thing. So you do 0.6 over 0.3 times 0.5, and that comes out to be 4, I think. Yep. So in that case, Q is less than K, and so that also tells you it needs to go to products. Okay, so kind of like a lot of different things going on here. You have to solve for K. That could be a problem in and of itself. If you were given the starting amounts or like says it adds an additional pressure, you could predict which way the reaction proceeds. And then the final thing would be you could actually solve it out. Now, I wouldn't put the actual solving it out on the test because the K is large, so you can't ignore any of the changes, and you end up having to solve the quadratic in that case. So we won't go ahead and solve through the whole thing, but just as like a reminder of the process, since it's going towards products, we would have minus X here and plus X there. So 0.3 minus X, 0.5 minus X, and 0.6 plus X. And then we would say K, which is 20, is equal to 0.6 plus X on top, 0.3 minus X on bottom, and 0.5 minus X on bottom as well. So again, K is pretty big, 20, so I can't get rid of those changes. And even if I did, it wouldn't make any sense. How there wouldn't really be anything to solve for anyways. So with the 2 on the bottom that you would have to FOIL out, you're going to end up with an X squared. So you would have to do the quadratic. So we won't go through and solve all of that because you won't have to do the quadratic on the test. Okay? Okay, so just a good reminder of like the various types of problems that you might see kind of all squished into one. Are there any other questions that have come up from chapter 16 before we kind of flip back? I think it's always good to do the previous chapter stuff because it's been the longest, but I just want to like make sure everyone's good on that before we move on. Okay, just think about it for 1 second. I'm going to pull up one of the practice exam questions because because there's 2 questions on there that I noticed this morning, and this happens all the time because I have to pull the questions from Pearson and I can't really rewrite them. But there were 2 on there that I want to clarify. I'll probably go in and just mark them correct for everybody, but I want to show you them so you don't get confused while you're actually doing the studying. Okay. Okay, so let me write it up here so that's, or I guess I could take a screenshot if I don't have a marker. No, there we go. So this one says you have an ionic compound that has a delta H of solution of negative 65. So let's just review what those delta H's were, so that it's a good reminder it was from the beginning of chapter 14. So when you have a solution forming, you can describe the energy in that 3-step process where you break apart the solute, you break apart the solvent, and then you mix them together. And then the difference between where you started and where you ended, that amount of energy is called the delta H of the solution. Like how much energy changed to form the solution. It's just that we're breaking up the forming of the solution into these 3 steps. There's one guess, there's 2 questions like this that they kind of, in my opinion, messed up, but I think I understand why one of them is messed up because they use a different term. So on these questions, this one says that the delta H of solution is negative 65. So it's something like how I have drawn. It's exothermic. The energy that's released from the mixing is bigger. Delta H of mixing is larger than the sum of the other 2. Okay, so like this is bigger than those 2 added together. That's how we know that this is exothermic, right? So, you know, maybe this one was like, I don't know, 200, and this was whatever that would be, 135. So that the difference was negative 65. Okay, so when they do this, I think they're mixing up this term we didn't use called delta H of hydration. And it kind of incorporates the mixing and the solvent. They certainly use that term on the next one. But the correct answer here is this one. It should say delta H of solute plus delta H of solvent. Okay? So that's why it's messed up, is they just say solute, and it should be solute plus solvent. And the way I know that is because it's exothermic, so the energy released with the delta H of mixing must have been bigger than the 2 of the delta H that was required. Like I said, I'll probably just go in and correct that for everybody, but I want you to understand so you're not confused if you're using this to study. Okay, this one was reading question 3. And then the other one that is very similar to this is this one. And the reason why this one is messed up is because they use this hydration thing that we haven't talked about. So it's the same thing where you're going to assume that solute means solute and solvent. So one that's near 0. So if it was near 0, they're talking about it's around this. So you're saying that solute and solvent are basically the same as delta H of mixing. And in their terminology, that's this one. Delta H of solute is close to delta H of hydration. So if you want to just mark it correct so you have it correct on there. But the concept is this stuff. We don't use that term delta H of hydration. We didn't use that at all. And the way we described it was by the sum of the 2 and comparing that to step 3. Okay, so if it's bigger, it's exothermic. If it's about the same, then it would, they'd be basically no change in delta H. Or if it was less than, then this would be endothermic. Okay, so any others on 16, just since I took that time now, and if you found anything. Otherwise, we'll just kind of like pick up. Does anybody have any particular topics they want to make sure we hit on 14? You want me to just come up with them? Okay, that's fine. Usually people are like, well, you wrote the test, so yes, please. Okay, let's see. All right, let's start with, I'm going to leave some of these notes to talk about it, but let's start with this one. Just as a way to talk about, so we talked about the concept of forming a solution, and then we talked about calculations to quantitatively talk about concentration, how much there is. And I want to make sure you guys realize, because when we first started it, it felt like a lot of different concentration units. But I want to summarize for you that they're not all that different. And you can, I wrote it down here, but you can also see it in the exam equation sheet. I don't like how they changed this. Okay, so like if you look at them here, it's got molarity. So this is on the equation sheet. It's not like something you have to have memorized. So you got molarity and molality, which we use both of those quite a bit because you use those in other calculations like osmosis or the freezing point depression, boiling point elevation. We use those a lot. And then you get fractions. So this one's mole fraction. We usually abbreviate that with an X. That's why that's there. Mass fraction and volume fraction. They all are basically the same thing. It's solute over solute plus solvent for all of them. But in this one it's moles, this one it's mass, and that one's volume. So you would use grams here. Technically you could use grams or kilograms because they'll cancel out anyways. Usually we use grams here and milliliters there. And then if you need, like if it says mass percent, that would be the mass fraction times 100. Or if it says volume, like parts per billion volume, you would use the volume fraction times a billion, okay? So just recognize that these are all very connected to each other, and then those two are kind of the ones that we use in further calculations. So even though it feels like there's a lot of different ones, they're all very tied together. Okay, so let's go back to the problem and do one of those because I don't think we did a ton that were like parts per million like that. So let's do this problem. A 1 liter sample of water contains this many grams of OH minus. Determine the concentration of OH in parts per million. Now, they really did need to say here parts per million by mass. Okay. When I write the exams, obviously I'm writing them, not Pearson. And so I'm like checking that kind of wording very carefully. So you're always welcome to clarify in the exam. I may or may not tell you. But usually stuff like this, you know, there's not going to be a confusion like I'm going to say by mass or whatnot. Okay, so take us a minute or two to work through this one, just as a good practice for getting you back into these types of calculations. I think I have one or two others if we want to do those as well. Okay. Okay, so because it's by mass, you're going to do the solute over the whole solution, so solute plus solvent. So they give you the mass of the OH minus, you can just put that in those two spots. And then for the mass of the water, you have to use the density, so 1 gram per mil. Like I think I told you guys this before, that's something you should know, that even if they don't tell you, water has a density of 1 gram per mil, okay? So 1 liter is 1,000 milliliters, and if it's 1 gram per mil, it's 1,000 grams, okay? So we're gonna stick, we're gonna stick 0.0, what is that? 0.56 in here, and 1,000 in here. And then because it's parts per million, we're doing the fraction times a million. And I already remember that one, it comes out to be 5.6 ppm. Okay, so I'm sure there's a couple more similar type ones in the practice exam. The other thing is, don't forget that because these concentration units are like a unit over another unit, often we use them as a conversion factor. So there's problems like that as well. And then kind of like the hardest ones are if they give you it in a particular concentration unit, like maybe they said what it was in molarity, and then you have to convert it to parts per million. So a few different types of problems that are related to that. Okay. Don't look at the answers before I have a chance to erase them. I did some of these earlier in my other class, so we'll do them again, but I don't want to give it away. Oh, I know which one I want to do. Okay, so freezing point depression and boiling point elevation, we did those at the very end. Dang it. We did those at the very end of chapter 14. So I want to do this one that kind of stretches a little bit. So I'm going to introduce the topic again, kind of remind you about it, and then let you guys have a shot at this one. So the two equations we use are really similar. Some of the practice exam problems will like this one, will ask you a question, but then they don't give you the constants. They're assuming you're not doing this as a test, you're doing it as an assignment. So they're like, well, you can go look up the constants. Obviously, I'm going to give you the constants in the question. So there's the KF and KB. Remember, boiling point increases and freezing point decreases. So these are going to give you the change. So if it comes out to be like 2 degrees, that means the new freezing point is -2. If this comes out to be 0.15, that means the new boiling point is 100.15. Okay, it doesn't tell you the new thing, it tells you how much it changes by. Freezing, it goes down, boiling, it goes up. And then the thing they're dependent on is I, which is how many ions there are. So in a covalent compound, it's just one. They're not technically an ion, it's just one unit. But in an ionic compound, you would then have to count up the number of ions. There's another question in here that does that, but maybe I'll just like remind you about it. So if you had copper chloride and sodium chloride and copper phosphate. Okay, so copper chloride breaks up into 1 copper and 2 chlorines. So I would be equal to 3 in that instance. Sodium chloride breaks up into 2, just sodium and chlorine. And then don't forget with polyatomic ions, like phosphate, that stays its own little unit, okay? So the phosphate is not going to break up. You would have 3 coppers and 1 phosphate, so a total of 4. Okay, so I know there's questions in the practice exam that require you to incorporate that. You don't have to do that in this one, but you know, it will be in others. Okay, so that's what the I is. And then M is molality. The little m is molality, which is moles per kilogram solvent. So moles solute per kilogram solvent. Okay, and then the constant. All right, so now take a look at this problem. And this one requires you to go a little bit further. So be creative, play around with it, see what you can come up with for this one. It tells you the freezing, they wants to know the freezing point of some water solution with solute in it, and it boils at 106.4. Okay, so take a couple minutes and then we'll talk through it. Okay, so I'm going to put a hint up here if you want it. Oh, put that constant in the wrong spot. Okay, so what they're expecting you to do here is use the fact that you know that the boiling point has increased by 6.4. So that's your change in temperature boiling, 6.4. Then the equation says I times M times the constant. Well, at this point is usually when people get stressed out because they're like, well, there's two unknowns. How do I know, whatever. You don't actually have to know what the I is, or for that matter, the M. You just need to know what that total is, because you're going to use that same value and plug it in here into the freezing point one. So you can think of it like that, like you're just solving for I times M, or just pretend I is 1, if that makes you feel better, and you're solving for the molality, okay? If it was 2, it's still going to work out because you're replacing I times M down here again, so it doesn't really matter, okay? So we use the boiling point 1 to solve for I times M. 6 times 4, 6.4 divided by 0.512. So I times M is 12.5. So then the change in freezing point is 23.25, which means the new freezing point is negative 23.25. Okay, and you should never, that's always going to be the case, where the change in freezing point is more dramatic than the change in boiling point. Let's do one with osmosis as well. I'm trying to think. There's a couple others we could do. Just yell out if you're like, oh, I know one that I really want to do. This one's okay. Let me see if there's, I think we had another one. Oh, let's do this while we're here. Okay, so the other thing we talked about near the beginning of the chapter was like dissolves like. So look at these molecules, and I want you to tell me if you think they would be more soluble in water versus hexane. And just to be clear, the formula for hexane, C6H14. Okay? So each one of those decide which is going to be more soluble in water or hexane. So we're looking for similarities in the structure of the molecule, the polarity really. So remember that water is polar. Hexane, because it's just carbons and hydrogens, must mean that it's nonpolar. So we want to look at those and see which are similar. So these two guys in the middle, those are also just carbon and hydrogen. Whenever you have just carbon and hydrogen, it's nonpolar. So these guys are going to be soluble in hexane. And then the other two, you've got OH groups on that one. So that's going to make it soluble in water. And then over here, it's just like all over the molecule. All these OH groups, this oxygen, that one, those are going to be points of polarity. So that one's definitely going to be soluble in water as well. And sometimes you'll get questions like, which is the most soluble in water? So like the more points of polarity, like that big, it looks like some kind of sugar. I was trying to guess. I was thinking lactose. Anyway, some sugar there is going to be more soluble in water because it has all of those different points where it can interact with the water molecules. Everyone's being very quiet. No questions? No, I guess that's the only osmosis one I had. It's like impossible to see these. Okay. All right, once you go ahead, the equation's there. It's in your exam equation sheet too. Go ahead and solve the osmotic pressure in atmospheres for this solution. Okay, so a hint when you're doing stuff like this to remember which constants to use and like what unit does temperature have to be in. When you go to find R in your exam equation sheet, the units will be listed with the constant. So like 0.0821 is liter atmospheres per mole Kelvin. It's listed there in the exam equation sheet. So it's telling you, this is going to give you, this is the right one, first of all, because the other R is joules per mole Kelvin. So that doesn't give you atmospheres. So you know it's that one. And then it also reminds you, because it has Kelvin in the constant, that reminds you that the temperature has to be in Kelvin. Okay? So use the constants to help remind you which one is appropriate and what the units of the other thing have to be in. Okay? All right, so both practice exams due tomorrow night. You can do, oh, you just had a question. You're going to ask a question. Ask a question.
Why is I 1?
Because it's a covalent compound. So covalent compounds, I is always 1, and since, yeah, all nonmetals. Good. All right, email questions. I can always make a video to like show you how to work through a problem. And exam on Wednesday.